My next presentation is the reactor analysis, because up till now I discussed the different types of reactor that we have. Now let us see how we can analyze the reactor. This is very important because analysis of the reactor is very important, and we will try to cover this. And before we go for that, we should know that what are the things actually present inside the reactor. That is, you see that inside the reactor there will be a starter I mentioned, and this is called agitator, and this is the impeller. And due to what is purpose of the agitator is to maintain the homogeneity in the reaction mixture, because so that, because particularly if you look at the microbial cell, they are the insoluble solid. And if you don't start it, then what will happen, that insoluble solid material will settle down, and if they settle down, then reaction will take only at the bottom part of the reactor, that the reaction will not take place throughout the reactor. So for doing so, we should have a starter. Now then I was talking that day that that one problem that we have with this biological system is the foam formation. And why the foam formation take place? Because most of the fermentation process, they are aerobic in nature. Aerobic means your microorganisms grow under aerobic in presence of oxygen. And I mentioned that it is little bit different as compared to the human system. Human system, we take oxygen from the air, but microorganisms they take the oxygen which is dissolved in the liquid. So naturally, until and unless the liquid, that oxygen that dissolved in the water, the microorganism cannot utilize for the growth and metabolism. That is very important. So so you have to start this that air continuously, so that dissolved oxygen concentration increases. That is the major bottlenecks of this process. Now when you do this aeration, that during the fermentation process, some protein formation is there. When protein and their air come contact with each other, they forms a bubble, that is called foam formation. And if there is a foam formation, then what will happen? It will accumulate at the top of the fermenter. Now if you allow it to accumulate, then what will happen is slowly it will go up and touch here. There will be a mechanical seal, and this mechanical seal is very crucial for any biochemical industries, because I told you in a very first lecture that basic difference between chemical and biochemical process is that in the biochemical process mostly we maintain the sterility in the reaction mixture. Because why sterility? Because we want to grow a desired organism inside the microorganism. We don't like to grow any other organism other than our desired organism in the reactor. So there should be perfectly airtight. And to make it perfectly airtight, the air seal this is designed, and if you allow the foam to grow, then it will enter into the mechanical seal, and as soon as it enter into the mechanical seal will be ruptured and the contamination will take place. So what we use the antifoam oil. We put a sensor here. As soon as it touches the sensor, the foam touches the sensor, then this is connected with some pump, antifoam oil tank pump connected with antifoam oil tank, that will drag the antifoam into the fermenter, so that your foam will be subside. Then we have other arrangement. You can see here that in the fermenter, I can tell you the sparger, that is a very important thing that we have. We pass the compressed air, and there should be a sparger here, and we have some jacketed system for passing the hot and cold to liquid to maintain the temperature inside the reactor. This stirring also help for maintaining the temperature inside the reactor. Then this air, what we pass, this is usually the sterilized air. We should not contain any kind of contaminants, and it goes like this. And when it goes like this, you can see it passes through a filter. And why it passes through a filter? The reason is that if there is a power failure, then what will happen? There is the compressor will be stopped. there is no airflow, and there is a possibility that the back suction of air. And so, if you do not have a filter here, then what will happen, the unsterile air will go inside the system and system will be contaminated. So, there should be a filter that we have at the exit, that air stream that is going out of the reactor. Then we have steaming, we pass steam, that is, suppose we because two type of sterilization we have, one we call in situ sterilization, another is in vitro sterilization. In case of a laboratory, we usually recommend, we have the small reactor, we can do this sterilization in vitro, but in case of big fermenters, usually we go for the in situ sterilization, means wherever the fermenter is located, there we do the sterilization. There this is the steam inlet, we pass the steam, and high temperature, high pressure development take place. With that, we maintain the temperature and sterilize as per our requirement. Then we have different monitoring system. We have temperature monitoring system. With the help of thermostat, we can monitor the temperature. We have pH probe, we can monitor the pH of the reactor, and there is the oxygen probe that will determine the dissolved oxygen concentration. So, these are the different arrangement we have in the reactor. We have the provision for acid and base addition in the reactor to maintain the pH of the reactor. The reason is that your microbial system are very sensitive to the environment. As your pH changes, that the growth of the organism might be hampered. So, if we want to control the pH, then we have this kind of arrangement, acid base addition system. Now, let me show you that reactor analysis, and for the reactor analysis we use a basic formula. This is called that material analysis. This is the rate of input equal to rate of output plus rate of disappearance plus rate of accumulation. Now, this is the equation is such a thing that here we consider one particular parameter to write this balance equation, because as for example, in a reactor we have substrate, we have product, we have in our microbial system we have cell mass. So, we have different type of, we have energy, some maybe some kind of energy point of view, it might be interesting. So, we can write the balance equation with respect to any such parameters. Suppose, as for example, if we want to write the balance equation, we can write the balance equation with respect to substrate. We can, so this is balance with respect to substrate, we call it substrate balance. If it is with respect to product, we call it product balance. If it is with respect to cell mass, we call it cell mass balance. So, we can write the different type of reactor. Now, first things that I am going to show you the batch reactor, and if you batch reactor, if you look at, it is very simple. That is, it is like this. It is the reactor we have. We have started here. This is the motor, and it is rotating like this. So, suppose A to convert it to B, this is like this. So, we put the substrate A at a time, we put all the material inside the reactor like this and allow the reaction to take place, and when the reaction is over, we take it out. So, what do we, so there is now if you look at this equation is the rate of input equal to rate of output plus rate of disappearance, rate of accumulation. Now, here what is happening, rate of input is 0 because we are taking the substrate at a time. Rate of output, you are not taking any output from the system. So, rate of output will be 0. What is the rate of disappearance? It is, we have seen when A is converted to P, how you can write the rate of disappearance, minus dCA by dt. This is the rate of disappearance, rate of disappearance. So, we can easily write this. So, this now why we are writing, we are multiplying by volume, because if you look at the concentration, this concentration is what the Ca is equal to maybe gram per liter. The gram per liter means per unit volume. But in the reactor, when you have reactor, you have some working volume. This is called V is called working volume. This is called working volume. So, so naturally this is to be multiplied by V, and so that you can in the calculation you can have all these changes that we have in this volume. So, that is why it is multiplied by minus R A is multiplied by V. Now, this is dCA V by dt. This is the rate of accumulation of A, that is taking place in the system, that with respect to time how much is the accumulation take place. Now, for constant volume, if the V we assume to be constant, liquid volume is constant, then we can have this equation dt equal to dCA by minus RA. Now, if here you see that you have the at t equal to 0, Ca is equal to Ca 0, then your integration is 0 to t, and you have Ca 0 to Ca dCA by minus Ra. Now, so here this is equal to T batch. T batch is the time required for the carrying out the batch reaction to convert substrate Ca 0 to Ca, and this is the equation. Now, here I want to point out a couple of things, that when you write T batch minus Ca 0 Ca minus Ra. Now, one thing is that if you look at the profile, concentration of profile, Ca concentration with respect to time is like this. Now, we have seen when A converted to B, what is the rate of reaction? Ca equal to K into Ca to the power n. That means it depends on the concentration of A, Ca. So, as the time passes on, you can see at different times, this is T1, this is T2, this is T3, this is T4, this is T5. So, at different type you have different substrate concentration, and since you have different substrate concentration, your rate of reaction will be different. Rate of reaction will not be constant, and since the rate of reaction is the constant, so so that is why we have here we have the integration sign. We have here we have the integration sign. So, this is like this. So, question comes then how we can find out the volume of the that time of the batch process. How we can find out? We can plot that if I plot 1 by Ra into Ca like this, and if your plot is like this, the correlation is like this, then if it is Ca 0 here and this is Ca, then the area under this curve we consider it as the T batch. This is considered as the T batch. So, this is how we can find out that we can easily find out graphically that how the batch time can be calculated like this. So, this is how batch time can be calculated, and next let us talk about the continuous reactor. And continuous reactor, basically we have two types. One is called CSTR, another we call plug flow reactor. Now, CSTR, as you know that I told you before also, that is very easy to operate, because we have a stirrer here. Main purpose of the stirrer to maintain the uniformity in the reaction mixture, and you pass the substrate here and take out the product from here. One end you are putting the substrate, another end you are taking out the product. So, your equation is same. Your rate of input equal to rate of output plus rate of disappearance, but here one thing I forgot to mention, that in case of batch reaction, since the substrate concentration keep on decreases with respect to time, so so this is considered as a very unstable reactor, because it is not a stable reaction, because steady state condition under no circumstances is possible in a case of batch process, since the concentration varying with respect to time. So, that is why it is the unsteady, is an example of unsteady state reactor. But if you talk about the steady state reaction, the primary requirement for this is that you have to maintain the concentration of the substrate uniform. If the concentration of the substrate uniform, then and only then it is possible to have uniformity in the reaction mixture. So, here your equation is the rate of input equal to rate of output plus the rate of disappearance plus the rate of accumulation. So, if you say under steady state operation, the rate of accumulation should be equal to 0. This is the very important, the rate of accumulation that should be equal to 0. Now, how we can write it? Suppose the rate of input, this is FA0. What is FA0? FA0 is the mole of A per time. I can always write the per unit time. This is mole of A per unit time, that is putting in the. But if you write that, we can this is equal to CA0 into FA. What is F? F is the flow rate. F we can the flow rate, volumetric flow rate. This is volume per unit time. Am I right? And this is what? This is concentration. This is moles of A per unit volume. So, when you multiply this, then volume will cancel, then mole of A per unit time. So, this FA0 is nothing but CA0 into F. So, here you see that that FA0, this is the incoming, this is rate of input, and output is FA, this is the output is FA, and what is the rate of disappearance? We have already calculated in case of batch reactor, minus RA into V. So, we can write this equation like this. The what is the FA? FA we can write that FA like this. We can write FA is how we can write FA is equal to CA into F, and CA is what? Yes, CA0 into 1 minus X XA. XA is the what is the that you know that what is the fraction of the substrate that is converted. So, we can if you do that we can replace this equation like this, then we will come here. This is the F by FA0 XA by minus RA, then we can derive from this equation like this. This very easily we can derive. Then XA, this I told you, this is CA0 minus CA by CA0, the fraction of A that is converted, and finally what what was the previous equation we have? You see, we have F by FA0 equal to XA by minus RA. Am I right? Now, what is the, I have already shown here FA0 equal to CA0 into F. So, I can write V equal to CA0 into F equal to XA by RA. Am I right? So, here I can write it F by F, V by F equal to XA into CA0. So, this is equal to minus RA. And what is this? What is this? This is XA into CA0 is the substrate that is converted, that is CA0 into CA divided by minus RA. So, this is very simple. Now, here if you look at the unit, this is V is the working volume of the liquid. This is your reactor, and this is the volume of the liquid. This is the volume of the liquid, working volume of the liquid. This is the volumetric flow rate. Now, what is the unit of volumetric flow rate? Volume per unit time. Am I right? And what is the unit of V? It is volume. The volume will cancel. This will be time, and this is called tau CSTR. What is tau CSTR? This is the space time. Why it is called space time? The reason is that the how long the liquid resides in the reactor, that is the space time. Because you are passing a liquid in the reactor, the question comes how long the liquid, because why you are interested for doing so, because the longer the liquid resides in the reactor, that longer will be the rate of reaction. Less time is resides in the real, less will be the reaction time. So, you know that it depends, that that is very important. And if what is our desirable thing is that our that space time should be as minimum as possible, because it is directly proportional with the volume of the reactor. Can you find out? This is directly proportional volume. If the space time is less, then volume of the reactor is less. Is space time of mode, volume of the reactor mode. Now when you do any kind of reactor design, then volume is a major constant, because when we produce any kind of product, our when our design criteria is that under what circumstances we can have the minimum size of reactor to get the desired amount of product. Because if the reactor size is small, our cost involvement in the process will be less. So that is very important. That is that is to be that plays very important role. So I shall show you when I shall discuss the other reactor, then I can make a comparative study and show you how we can really go design the reactor and select the reactor, which reactor will be better for our system. Now next reactor that continuous system, I am going to discuss what you call plug flow reactor. Now now before that let me discuss this one, because last time I discussed the batch process, that when you plot, because in the tau CSTR you can remember we derive the equation like this: CA0 minus CA minus RA. Okay, and in the batch process what we have designed, batch process, we have we derive this equation minus dCA minus RA. Am I right? This is equal to CA0 into by. Now here suppose this is CA and this is minus 1 by RA. You have this kind of plot. Now in case of CSTR system, because this will be the CA and this is CA0, this is the CA. So area under this curve, because as CA, what is the rate of 1 by RA? This one. So what is that? CA0 minus CA, that is length, minus 1 by RA is this one. So it is the area of a rectangle. Am I right? This is area of a rectangle is nothing but you have tau CSTR. So this is how it has been shown here in this figure. You can see minus 1 by RA plus CA when you plot, and if you have this kind of correlation, and graphically you can find out also that what is the space time, that you can easily calculate. Okay. Now let me talk about the plug flow reactor now. Plug flow reactor, I told you it is kind of tubular reactor, and you know the tubes that you can easily find out the tube. The liquid is flowing through one end to others, and we plug flow, basically we assume this is the velocity gradient across this cross section should be minimum. That is the plug flow is it's a kind of similar to the piston flow. Piston flow is considered as the ideal flow, you know that. So this is like this. So here this process also we have the same equation we use, that is rate of input plus rate of output, rate of disappearance plus rate of accumulation. Now question comes how we can analyze this reactor. This reactor we can analyze. We first we assume here this is, since it is a continuous process, here also there is a possibility to attain the steady state. Now to analyze the reactor, what we do, that we assume a differential segment of this reactor. We just cut a portion of the reactor, and then we do the balance across this segment. Like this here, this segment we know let us assume the volume of the segment is dV, and Fa is the input that moles of A that is entering into the system, and whatever change is there dFA. So Fa plus dFA is what is the outcome is going out from the system. Now why it is plus? In case of product it should increase, in case of substrate it may be negative. So it is that is why we consider it the dF. Now liquid is flowing like this. Now what is how this equation we can write? This is Fa equal to rate of input equal to Fa plus dFA. This is output. This is the two things we have, and rate of disappearance is minus RA into dV. Now if you analyze this system similar as we have done before, we can come across this equation, very simple equation we can derive, and ultimately we can find the same equation that we have seen in case of batch process. T batch process we have also seen. This is now question may be asked that why we have the similar type of question. The basic main reason is that if you look at in the batch process, if you plot CA with respect to time in case of batch process, then what is happening? That that substrate concentration keep on decreasing with respect to time. Now in case of plug flow reactor, this is distance, because that liquid is flowing from one end to others. This is like this. So this is CA0 and this is CA. So it is flowing like this. This direction is flowing. This is with respect to distance. So you can take the sample at different location. Here you can take. So here CA value will be different like this. If you plot this, you will also find this. So you can easily find out similar type of correlation. This is with respect to time. This is with respect to distance. That is why that in a tau plug flow reactor is equal to minus CA0 into CA dCA minus RE, and it is same at T batch. Now I was talking about the selection of the reactor. This is very important. Suppose how you select that reactor. Suppose I want to operate, because we always operate the continuous system. The reason is that rate of product formation in the continuous system is much more as compared to batch process. So suppose we have plug flow reactor, we have CSTR, and we have the correlation between 1 by RA and CA is like this. This is CA0 and this is CA. Now in case of plug flow reactor, this is tau plug flow reactor, space time of the plug flow reactor, and in case of CSTR, this area under this curve will be tau CSTR. Now tau plug flow reactor here is much less as compared to tau CSTR. So what we will go for tau plug flow reactor. Now situation will be different when we have the correlation in other way. Suppose we have correlation like this. This is minus RA by CA. Now here we have CA0 and this is CA. Now the area under this curve will give you the value of tau CSTR. Am I right? And but the area under this we will give tau plug flow reactor. Now here tau CSTR is much less as compared to tau plug flow reactor. So we will go for tau CSTR. If your correlation is like this, this is how we can select the reactor, which reactor we should select for a particular process, because our target is to get the minimum time required to get the desired amount of product. Thank you.